Alright, so in this video I'm going to look at the 2010 Unit 4 Section A, so the multiple choice questions. So I'm going to show you how you get to the solutions for each of them and also show you the way I think through the questions and the way I eliminate answers, that kind of thing. Okay, so the other thing to note is that the Unit 4 questions, they rarely change, so like the first ones are usually applied mechanics and the later ones tend to be magnetic fields, that kind of thing. And you'll see that as you work through the different ones. So let's get started straight away. So we've got a graph showing the variation of time with force, and it's looking for the area what the area of the graph represents. So the area of a force time graph is the impulse or the change in momentum, and you can see that because when you find the area, you're effectively multiplying the variables with force times by time, which would be a delta momentum here times that one. So they cancel, so it just gives you a change in momentum. So you can check that if you disagree, but otherwise you can just remember that the area is an impulse or a change in momentum. Okay, so we've got water of density 1,000 kilograms per meter cubed, flows out of a garden hose of area 7.2 times 10 to the minus 4 meters squared at a rate of 2.0 times 10 to the minus 4 meters cubed per second. How much momentum is carried by the water leaving per second? So what we're trying to get to is momentum per second. So the unit we want would be kilogram meters to minus 1, but then divided by second, so kilogram meters to minus 2. And the way we're going to get that is we essentially need the mass per second, and we're going to times it by the velocity, so the meters per second. So what we need to do first is work out what the velocity is. So we're going to get the velocity by doing the volume per second divided by the area, which is going to give you 2 over 7.2 because they're both multiplied by 10 to the minus 4, which let's keep that as a fraction, would give you 5 over 18. And the mass per second is going to be the volume per second times by the density, which is going to be 2.0 times 10 to the minus 4 times by 1,000, which gives you 0.2 kilograms per second. So we're going to times that by 5 divided by 18, gives you 1 over 18, which gives you 0.055, which would be 5.6 times 10 to the minus 2. So these kind of ones crop up quite a lot, so the way to get to them is to think about the units of what you're dealing with. Usually if you have volume and area, you're going to end up calculating the velocity, like I've done here, and you can also work out the mass per second using the volume per second and density. So let's move on to 3. Which row in the table correctly shows the quantities conserved in an inelastic collision? So an inelastic means total kinetic energy is not conserved, so some is wasted by transfer into other forms. So mass is going to be conserved, so we can eliminate B straight away. We're not talking about nuclear physics here, so we're not going to be dealing with something where mass is not conserved. Momentum is always conserved, so because there's no external force acting, so we can eliminate A as well. Kinetic energy we know is not conserved, so that we can eliminate C, and then we get to D, and we know that total energy is always conserved, so we can keep that one. So angular speed of a point on Earth's equator. So the key here is to remember that the time period of Earth is 24 hours, so it spins once every 24 hours. So it's going to be converting that into seconds, and let's type that in and get 24 at 60 times 60, which is 8640. And we know that the angular speed is 2 pi over t, which is 7.27 times 10 to the minus 5. So that's going to be number A, and like this crops up quite a lot, so it's a useful thing to remember so you can check you're getting the right answer. 5. Which one of these does not involve a centripetal force? An electron in orbit around a nucleus? Absolutely it does. It uses the electromagnetic as a centripetal force, so that one is. A car going around a bend uses friction as its centripetal force, so we can eliminate that one. An alpha particle in a magnetic field travelling at right angles to the field. Absolutely, that would involve a centripetal force because we know the force is perpendicular to the motion, which is a centripetal force. So we already know the answer will be D because we've eliminated the others, but if we remember, the force from an electric field would be the same regardless of direction of motion of the travel, so we know that would not be a centripetal force. The force isn't dependent on the motion of the object. Okay, let's scroll down. Which one of the following gives the phase difference between the particle velocity and the particle displacement in SHM? So the velocity is the gradient of the displacement. So if the displacement's a sine graph, it would be a cosine graph, which is 90 degrees or pi over 2 out of phase, which is that one. A mass hangs in equilibrium on a spring. The mass is made to oscillate about the equilibrium position by pulling it down to its vertical SHM system and releasing it. Time for M to travel back to the equilibrium position for the first time is 0.5 seconds. Which row is correct for these oscillations? So the amplitude is going to be 10 because that's the amount we initially displaced it, so that's going to be the maximum displacement, so we can get rid of those. And it takes 0.5 seconds to get to the equilibrium position, which is a quarter of a cycle, so it'll be 4 times that, so it gives you B as your answer there. Okay, which one of the following statements concerning force vibrations and resonance is correct? An oscillating body that is not resonating will return to its natural frequency when the forced vibration is removed. That's possible, so let's check the other ones. Okay. At resonance, the displacement of the oscillating body is 180 degrees with a forced vibration. No, it's not. It's 90 degrees, or pi over 2. Pendulum with a dense bob is more heavily damped than one with a less dense bob of the same size. No, damping is nothing to do with that. That's not going to change. Remember, mass, everything's independent of mass, so no. Resonance can occur only in mechanical systems. Rubbish, you get all sorts of resonance in things like bonds and all those other things. So yeah, coming back to it, absolutely. Stuff returns to its natural frequency if it's not resonating when you remove the force vibration. That's fine. 9. Two identical spheres exert a gravitational force F on each other. What is the gravitational force between the two spheres each twice the mass of one of the original spheres when their separation of centres is twice the original? So we've got two spheres, each exerting a force F, and we know the force would be gmm over r squared. So they're both their masses are doubled, so effectively we've times the top line by 4. And the separation is double, but double times 2 squared, so you just end up with the same force because both top and bottom line are multiplied by 4. A planet of mass m and radius r rotates so rapidly that loose material at the equator only just remains on the surface. What is the period of rotation of the planet? Okay, so the force acting on it would be gmm over r squared, and it's just remaining in circular motion. This looks like we've got a 2 pi in there, so squared r. Actually, let's be consistent with our uses of r. So we know that gm is omega squared r. So omega squared is gm over, that'd be r cubed, which means that 2 pi over t is is the square root of gmm over r cubed. So flip both sides over, take the 2 pi to the side, you'd end up with 2 pi root r cubed over gm, like when you end up rearranging that, because we're going to flip it over, so the r cubed would end up with the top line. So the only one with an r cubed on the top line is d, so we know straight away, and we've still got all the other components there as well. Okay, so the radius of a certain planet is x times the radius of the Earth, and its surface gravitational field strength is y times that of Earth. Which of the following gives the ratio mass of the planet to the mass of the Earth? Okay, so the ratio of field strength, so we want EP over E of the Earth. And we know that that ratio is equal to y. So essentially, in terms of how we'd calculate it, it would be g mass of the planet over the radius of the planet, which we'll put as x radius of the Earth, or squared, divided by g mass of the Earth divided by the radius of the Earth squared, and that's all going to be equal to y. So this term here is going to cancel with that one, that term cancels with that one, so you end up with mass of the planet over the mass of Earth, but we've still got this x on the bottom line, so when we take it across we have x squared y, and that's going to be answer B. So essentially you're just putting in the expressions for the field strength, but putting them in terms of things that can cancel out, so having them both in terms of the radius of the Earth. Which one of the following could be a unit of gravitational potential? So potential, remember, has the units joules per kilogram, because it's gravitational potential. And remember, a joule is a force times a distance, so that would be Newton meters per kilogram. Remember, newtons have the unit kilogram meters per second squared, so that would be meters squared s to the minus 2, and the kilograms would cancel. Okay. Could be, so newtons, no. Joules, no, because it's joules per kilogram. We've got newtons per kilogram, no. But we've got joules per kilogram. Absolutely fine. You've got two particles at a distance d apart, one with charge plus q and the other of minus 2q. So the force F, each particle is then given an additional charge of plus q, and their separation is increased to a distance 2d. Which of the following is the force that now acts? So the force before would have been 2q squared over d squared, and then but they would be multiplied by a constant. So the new one, it would be if you increase q by q, you'd get 2q. If you increase minus q by q, you'd get minus q. And we've doubled the distance, so we'd end up with k 4d squared. So what's that? So we end up with 2q squared over k 4k d squared, which is a quarter of what we had before, which is, so that's going to be f over 4 there, and one's going to be a positive plus 2q, the other one's going to be a minus q, so it's going to be an attractive force of f over 4. Okay, which one of the following statements about a charged particle in an electric field is correct? No work is done when a charged particle moves along a field line. So along a field lines go from plus to minus, so as it moves along it's either being attracted or repelled, so a force is acting, so that's wrong. No force acts on a charged particle as it moves along, rubbish. because it's charged, so that it's going to be either attracted or repelled by one of the positive and negative charges. No work is done when a charged particle moves along a line of constant potential. Well, if it's potential and therefore potential energy doesn't change, that means no work is done. So yes, that's going to be correct. No, if it's along a potential line, there's still a force, it just not changed the potential, so that's rubbish. So we're left with C. Two parallel metal plates separated by a distance d have a potential difference v across them. What is the magnitude of the force acting on a charge q midway between the plates? So the field strength is v over d. And the force is going to be what the field strength times the charge you put in it. So v d q, and so we're going to end up with expression B there, because it's a uniform field, so we can use a uniform field equation. Which one of the following statements about electric field strength and electric potential is incorrect? Potential is a scalar quantity, so potential is a type of energy, so that is true. Field strength is a vector quantity, that field strength is like a force, so absolutely it's a vector quantity. Potential is 0 whenever the electric field strength is 0. So remember, field strength is the potential gradient. So you can have a gradient of 0 when the actual thing, so like if we have a graph here, so say we had potential here. If potential remains constant, that would mean that the field strength was 0, but the potential was not. So that is not correct. And the potential gradient is proportional to field strength. Yeah, so that one is correct. So we're left with C. You can get that one by eliminating more than anything. An alpha particle travels towards a gold nucleus, and at P reverses its direction, so that's the distance of closest approach. Which one of the following statements is incorrect? The electric potential energy of the electric potential energy of the alpha particle is maximum at P. That is absolutely true. It is, because all the kinetic energy has been transferred to electric potential energy. Kinetic energy is at minimum. Yes, it is, because it's all been transferred. So hang on, these ones are both true. Total energy of the alpha particle is 0. Nonsense, because it starts with kinetic energy. So that's not true. The total energy of the alpha particle has a constant positive value. Yes, so it starts off with kinetic energy, so we know and then it's going to be transferred to electric potential energy. They're both positively charged, so the potential energy is going to be positive. So yeah, that's going to be true. So C is the correct answer to that one. The graph shows how the potential difference across a capacitor varies with charge stored. Which one of the following statements is correct? The gradient of the line is the capacitance. So we know the equation Q equals CV. So if we have V on its own, it's going to be like that one. So we are looking for the correct one, so that's not true. The gradient is energy stored, rubbish. The area is the energy stored. The reciprocal of gradient equals the energy stored, rubbish. The reciprocal gradient is the capacitance, yeah. We've just shown that there when we put it into y equals mx plus c form. An initially uncharged capacitor of capacitance 10 microfarads is charged by a constant current of 200 milliamps. So if we did a charge versus time, if you're charged by a constant current, that's going to look like that. After what time will the potential difference across the capacitor be 2000 volts? So what we need to work out is the charge that corresponds to 2000 volts. So we know Q equals CV, so that's going to be 10 times 10 to the minus 6 times by 2000 equals 20 times 10 to the minus 3 coulombs. And if we're charging by a current like this, remember Q equals IT, so T equals Q over I. And so if we do 20 times 10 to the minus 3 or 2 times 10 to the minus 4, and we divide that by current, so 200 times 10 to the minus 6, that gives us a time of 1 100 seconds, so answer number B. A 1000 microfarad capacitor X and a 100 microfarad capacitor Y are charged with the same potential difference. Which row A to D gives in the table gives correct ratios of charge stored and energy stored by the capacitors? Okay, so capacitance is the charge stored per unit volt. So if they're charged by the same potential differences, the charge would be in the ratio of their capacitances. So X would be able to store 10 times as much as Y. So you'd end up with 10 on the top in the ratio. So that's going to be wrong. And if V is the same, energy stored is going to be half CV squared. So if you have 10 times the capacitance, again you'll have 10 times the energy, so that gives you this one down here. A current of 8 amps is passed through a conductor of length 0.4 meters and area of this one. It's got that many charges per meter cubed. When the conductor is at right angles, the magnetic flux density is 0.2 Tesla, and it experiences magnetic force. So what is the average magnetic force that one of these electrons? So we can calculate the total force, and we know that's for this many electrons, so we can do it for one. So first, let's calculate the force. So we're going to do BIL, because it's perpendicular, so it'll be 0.2 times 8.0 times 0.4. So let's just calculate that before we go any further. So 0.2 times 8 times 0.4 is 0.64. So we need to work out the total number of electrons. So we know it's that many per meter cubed, so we need to work out how many meters cubed they are. So the volume would be the area times the length. So that's going to be 1.0 times 10 to the minus 6, which is the area, times 0.4, which is the length. 1.0 times 10 to the minus 6 times 0.4. So that's 4 times 10 to the minus 7 meters cubed. So the total number is that times the number per meter cubed, so 8 times 10 to 28, which is 3.2 times 10 to the 22 electrons. 0.64 divided by that answer would give you 2 times 10 to the minus 23, so answer D. So what we've got here, we worked out the force, we worked out the number of electrons, so we divided those to find the force per electron. Okay, so 22. An electron moves due north in a horizontal plane with uniform speed, enters a uniform magnetic field directed due south in the same plane. Which one of the following statements concerning its motion of the electron in a magnetic field is correct? So, a charged particle only experiences a force if it's at an angle to the field lines. If it's parallel, it experiences no force. So it will continue its original direction with its original speed, because when you travel parallel, there is zero force. Particles of mass m, each carrying a charge q, traveling with speed v, enter a magnetic field of flux density b at right angles. Which one of the following changes would produce an increase in the radius of the path of the particle? So we want to increase the radius, so we're going to be in a circular motion. So at that point, so the centripetal force would be BQV, which we know would be to mv squared over r. So we can cancel one of those. So we know RBQ is mv. Well, so if we want to increase the radius, we need to either increase one of these two or decrease one of these two. So increasing Q would not help. An increase in M would absolutely help. Decrease in V would not help you increase the radius. and increasing B would not help you, so increasing M is the only thing that would, remembering that we take this over to the side, so it's on the bottom line. So we want to make those two smaller, or the top line bigger, to increase R. So essentially all we've done here is just equate the force of a charged particle with a centripetal equation. The magnetic flux through a coil of n turns is increased uniformly from 0 to a maximum value in time t, and EMF E is induced across the coil. What is the maximum value of magnetic flux through the coil? So, if you remember, an EMF is the rate of change of flux. So there's one coil, so it will just be so we've got N. And we're trying to find the maximum value of the magnetic flux, which is this one. So it would be E T over N. So flux is BA, and we know EMF is the rate of change of flux linkage, which is BAN over T. So then we rearrange that so we can get BA is equal to that, which gives us answer A. An aircraft of wingspan 60 meters flies horizontally at a speed of 150 meters per second. The vertical component of the electric field is 1.0 times 10 to the minus 5t, which is perpendicular. So we want the EMF. So what we've got. So we can calculate the swept out area, which would be 60 times 150. So that's your A per second. So we need to multiply that by B, which would be this one. That would give us, when we calculate it, an answer of 60 times 150. That's what it's 0 instead of 5. That gives us 0.09 volts, which is answer A. So here what we've got is the swept out area, so your area per second, and then we've got B, so you're getting BA per second, the rate of change of flux, so that's your EMF there. Okay, so that concludes the 2010 Section 8 multiple choice questions. I hope you find that helpful to solve them. Please do post any questions if you have them, having watched this video and you're not sure of anything.